Okay, can you guys you're seeing my my presentation now? Okay, great. Um, hey everybody. Hope everyone's having a good HackNC. It's been a lot of fun watching what people are doing. And my name's Ryan Bergman, and I work for John Deere Intelligent Solutions Group. And I'm going to give a little presentation here on what a little pun of farm to tablet agronomic data processing at John Deere's, and talk a little bit about what we do and how we do it, and some of the interesting things and interesting problems that we have. So, just a little bit about John Deere. If you don't know who we are, um, I'm going to try to get this. I don't know if I can get this to be more full screen, but well, we'll just roll with it. If you don't know who John Deere is, John Deere is a company. We make farm equipment and construction equipment, forestry and lawn mowers and such. Kind of best known for our tractors and agricultural equipment. Um, but we do just as much construction, really. And the area that I work in mostly concerns itself with ag. We're starting to do a little bit more with construction these days, but the purpose of the company really is to be committed to those who are working um, with the land, whether that means you're farming or you're moving earth. Um, and we're really try and have a goal of creating a sustainable environment for agriculture for the future. We have ever-growing population, and that population is more and more in greater areas of the world that human beings didn't always live in as great a numbers as we live in today. And so we got to get, in order for those people to be able to be fed, um, we need to increase the amount of output we can get from our farms. And that doesn't just mean in the central United States. It means all across the world in different kinds of environments and different kinds of climates with different kinds of soil and different kinds of plants. We need to be able to feed the world and have that be done locally, and have that be done sustainably. Um, and so there you go. It's the 21st century challenge. I forgot I had that slide. So a little bit about me. I'm a software developer. I am my technical title is senior product engineer. Um, I don't actually have a degree in computer science. My degree was in community and regional planning from Iowa State University. Um, and I kind of came into software development starting as a hobby, and then just kind of started doing it during the first tech boom in the first .com phase in the late 90s. Um, I've been with John Deere since 2011. And I do a lot of speaking, a lot, especially within the Agile and XP and DevOps communities. Um, so John Deere Intelligent Solutions Group is a division of John Deere. We're mostly, as I said before, we're mostly associated with the ag stuff, but we're starting to do more and more with the construction. We concentrate on the high tech end of the software we build, so that goes onto the tractors. So everything from the displays on the equipment and to cloud computing and machine learning and all kinds of fun stuff. So the headquarters of John Deere is in Moline, Illinois, but kind of the pseudo headquarters of the Intelligent Solutions Group is in Des Moines, technically a suburb called Urbandale, but it's Des Moines, Iowa. We also have offices in San Francisco, Torrance, Kaiserslautern, Germany, and Pune, India. And so what we're going to talk today is, how do we get data from the farm and get it onto a tablet or phone or a computer, and what are all the different kinds of systems that are involved in that, And I'll try to talk a little bit more with this group. A lot of times I give this presentation, just to maybe business people, talk a little bit more in depth about the actual tech and the kind of stacks we use. You might find interesting. So what it starts off with, and the first thing that ISG started working on, probably around 2000, is autonomous vehicles. So I know a lot of people like Tesla and Google and others are working on autonomous cars, but we've been producing autonomous tractors or semi-autonomous tractors for quite a while. And it's maybe a little bit less of a challenge to get a tractor to drive back and forth across the field than it is to get a car to navigate the streets of San Francisco. But you'd be surprised at how challenging it can be, especially when you consider how accurate we need to get. So the goal really is tractor goes out in the fall and it's going to plant rows of whatever the crop is, say corn, and then in the fall we need to come back with a combine and we need to harvest those rows in the exact position that they were planted, and that means we have to get within 1 inch accuracy or less for the equipment. Now if you've ever looked at your phone when you're walking around or trying to get an Uber, you will notice that your accuracy on your phone is not very good. You kind of float all over the place. You're in the middle of Starbucks when you're standing across the street from it or something. Um, so, in order to increase that accuracy, we use very accurate satellite receivers and we use RTK, real time kinematic positioning, with triangulation in order to get that. So the equipment has a satellite receiver that is much more accurate than your phones, and then there might be other receivers, say on the implement, like the planter that's being pulled. There might be hopefully other ones that are, say, on top of a barn or on a telephone pole or something like that, in which we can provide that kind of triangulation to be able to get our accuracy for our equipment as tight as possible. We, oops, let's see. Um, we kind of maintain, with the help of our dealers, one of the largest base station networks in the country. So this is kind of a satellite view, or just a map, really, of all of our base stations. Those little green dots, those light green dots, are show our coverage area. So our dealerships go out and they take these base stations, which is basically the same thing as when you saw that yellow hat-like thing is satellite receiver, and we'll go out and we'll mount those on the tops of barns and telephone poles and anywhere we can get them. As you can see, we have pretty good coverage throughout the kind of the corn belt, if you will, or the corn and soybean belt of Iowa, Illinois, Nebraska, Minnesota, Indiana. But we're always growing this network, and we'll grow them anywhere that we can expect to have large scale autonomous vehicles in play. And the reason we do this, the reason why we want to get this accurate, is because it helps the farmer um, get the most out of their land. So we can get very, very accurate with where exactly we're planting, with the distance between the plants, um, either between the plants in a row or actually the distance between the rows themselves, which have gotten smaller. So we're actually been losing land to urban sprawl um, and climate change that makes us so there's maybe not as much land as we used to have um, to be able to plant crops. And so the only thing we can do is put more crops into that land, right, into the land we've got. And with proper crop rotation and soil conservation techniques, this is fine. We can cram a lot of plants into it, and as you can see, we can get very accurate with those rows. And there's also, the farmers love it because it's very pretty, to be able to get those super straight rows that are super lined up, and then get that edging, so we get the most plants onto that land. Um, now, when it comes to harvesting, the same thing applies when it comes to the accuracy of those autonomous vehicles. So, and at that point, also, when you're harvesting, unlike planting, where you're probably out there with just one piece of equipment, maybe you have couple of tractors, but they're really not interacting too much. You can have two people on either two sides of a large field, and they can start, and they just kind of meet up in the middle. When you're harvesting, you got a lot of stuff going on. A combine can't actually hold all of the grain from a field. You got to offload that into a grain bin. And so here in this picture, you can see there's a combine and a tractor, and the tractor is hauling a grain bin. Um, those vehicles are talking to each other through kind of a shortwave radio system. It's basically Wi-Fi. So when the equipment comes into the field, they basically start a little LAN party. Um, and the pieces of equipment can talk to each other, and they know the position of one another. So in this scenario you see here, that tractor, we make people sit in the equipment. You can't just um, they're not fully autonomous, and that someone has to be there, but they're not really doing much other than paying attention and making sure that everything is safe, which is why we want to have them there. But in this case, that combine and that tractor are basically driving themselves. The tractor is pulling up, and it's moving that grain cart maybe backwards and forward, along with the combine moving the arm of that auger, so that you can efficiently fill up that grain bin. This is a very stressful thing to do if you're two human beings and you got to line up perfectly. I mean, imagine if you're driving that tractor and you're trying to look back over your shoulder and make sure that that all the grain's going into the bin, you're not spilling anything, and then you're always also trying to look forward and make sure that you're not going to have to turn, or you're not going to hit something or something like that. The drivers can stay focused on safety, um, and let the equipment, for the most part, do all of the hard work. Then we take that equipment, when we're taking all that data, and again, when you look back on this other screen, that combine is, it's harvesting that in this case corn, and the word combine is because it's a combination of activities. So we're picking the corn, and we're shucking the corn, um, and we're removing the seed from the husk, and then we're putting it up there, and we have all kinds of sensors in it, so that we know what the volume of the seed is that's coming out from any particular part of the field, and we know what its moisture content is. Um, and so all that data is being collected, and at the same time it's being collected, we're sucking it up into the cloud. Um, and that's done through some telematic equipment that's on the equipment. This is the display, the default display. Now, if you go into a lot of large equipment that farmers are using, um, you'll see a lot of them have it all tricked out, and they've got like three or four. They might have two John Deere displays. They might have a couple of iPads, and all of that equipment, and all of those. Maybe they have their phone, and then there might be someone at home, um, maybe someone who owns the farm, and they're having someone do the equipment, the work for them. They can watch what's happening from their home, and so that's all happening through just normal cellular connections. So all of our equipment basically comes with what is effectively a cell phone, um, inside that silver thing you see there. That's called an MTG, and we're taking all that data off of the CAN bus, and we're sending it up through cellular network. Now we have really, really big antennas on the equipment, so we tend to also get better reception than, say, your cell phone in the country. Um, it may come as a shock, but when you see those really big maps from Verizon and AT&T and such, showing, basically it looks like all of America is covered, it doesn't work as well always when you're out in the country. Or sometimes you might have a really, really bad connection. You might be down to, like, you know edge or something like that. And so all of our protocols for sending data are with that in mind, that we're not always going to have a connection. Sometime the connection is going to be wobbly. It's going to go in and out. You're going to go down to the bottom of a hill and you're going to lose cell connection. You're going to come to the top of the hill and you're going to get it back. And then maybe when you have it, you're not going to be able to push much data over. So we are really big on compressing and making that data format and exchange as efficient as possible so that we can get the data in and out. We don't want to send it up over satellite because that gets really, really expensive. And we're necessarily can't push a ton of data that way anyway. So how much data are we talking about? Well, when you take something like the ExactEmerge planters that we have, that's 32 rows. So that tractor is pulling a planter that plants 32 rows at a time. That's a lot. We don't actually keep track of necessarily the geographic position of every seed. We are sampling it at 5 hertz, and we can go even faster than that. We go down to 1 hertz sometimes for high res. And so we have 15 sensor readings of 5 hertz. That's 24,000 measurements a second. And that's happening all at once. And then keep in mind that we are a very cyclical kind of business. We do a lot of processing in the spring. We do a lot of processing in the fall. We don't necessarily do a ton in between those, but right now it's October and it's dry, and we've got tons of people out within the Corn Belt, all out there harvesting at once. And sometimes in the spring, you'll have a wet spring, and then all of a sudden, you'll finally have a week where it's really dry, and everybody will go out and plant at the same time. And so we've got to take into account that that we're going to start getting data, massive amounts of data, and it's just going to show up one day. And so all of our processing that takes this into account is very auto-scalable. Most of that stack for the data as it's coming in is on our data processing. It's mostly JVM based. It can be either Java. There is a lot of Scala. I will say that we've started to see, we got really big into Scala maybe about 5 or 6 years ago, kind of when it was a bit of the hot thing. And now that Java's kind of caught up as far as with its functional programming aspects, we don't see as big of an advantage to using Scala anymore. And you're starting to see a lot of those services, if they're going to go over a major overhaul, we might rewrite them in Java. But there's still a fair amount of Scala too. The front ends of most of our stuff are Node.js, React for the most part. But those streaming, what we basically do is we stream all of that data in through a series of what is essentially streaming queues, and that scales up and down for the season. So on Christmas Day, I might not have very much going on. I had there was a service that I worked on at one point, and on Christmas Day, it had like 2 instances of it running. And during peak time, I think last spring, it had over 500 instances of it running. And it was just chugging along, chewing through all of that. And so this can show you, like, we can actually take a look at this when it's a busy time like it is today. It's pretty nice out right now. I'm looking out the window and it's sunny. I imagine there's a lot of harvesting going on right now. This is a snapshot from last year. Each of those yellow dots represents a piece of equipment that's streaming in data. We see there's some down in Brazil. There's someone up in the middle of the night in New Zealand. And you can watch this like kind of light up across the globe as the Earth moves. So, if you'd rewound this from where it was, maybe 5 hours, you'd see a lot more going on in Europe. at the time. So each of those dot represents a machine, and that this whole thing represents 5,000 active sessions. There's 5,000 people on Earth streaming in data to us right at this exact moment, and that can go up from minute or down from minute to minute. That's 12 million measurements per second and 720 million measurements in 60 seconds. So that's a lot of data that's processing through. And so we take that and it goes through a series of different pipelines, and what results is different kinds of maps, different kinds of reports, different kinds of things that the farmer is going to be able to use. So they're going to get detailed maps and reports about their operation. So you can see here in this field, green is higher harvest, red is lower. And so then they can go back and they can work with an agronomist or a seed expert and say, hey, what's up with this field? What's up with that red area in the lower right hand corner? What's my problem there? And that agronomist might, go out and do some soil sampling. They might say, oh, this is really, it's too acidic. It's not acidic enough. Let's figure out what we need to do to get the pH balance correct for that soil. The This data can go directly to that agronomist, and they can use their own tools to write what is essentially a prescription. And that prescription might say, down in the southeast corner, we're going to add a bunch of lime, and somewhere else we're going to do something else with it. And they'll send that as an electronic document back to the farmer. That document, that prescription, can be loaded into, say, a sprayer or some kind of other fertilizing machinery. And then the sprayer could go out and it could drive anywhere in that field. It could do little circulates in the field, and the sprayer would spray only exactly what it needs, where it needs to spray it, and provide only the exact amount of fertilizer that it needs. And so that saves the farmer a lot of money because inputs are expensive, and and also time, because he doesn't have to, or she doesn't need to have to figure out where stuff needs to go in a very precise sense. So how we do this, how we figure out like where on Earth we're doing things for these maps, we use Google's essential tile projection. If you've never noticed this, if you're ever on Google Maps and you zoom in and out, you'll see kind of those squares popping as you go, especially if you have a slower connection. Think of the entire world as if the entire globe is zero. It's one giant square, even though it doesn't stretch out into a square very perfectly, being that it's a globe. But you could take that square and you could cut that into 4 squares. And then you could take that square and you could cut it into 4 squares. And each of those times you cut it up, it's a different level. And when you get down to the typical Google Maps, if you're looking at your neighborhood, you're probably somewhere around 12 to 14 levels. And we actually go quite a bit smaller than that. We keep chopping that box up. And so into, I think 3x3 is, we've changed a few times. So 3x3, I think, is the standard we're using right now, 3 foot by 3 foot section. So if you take this real field as an example, it's 48 acres in the middle of Illinois, has on that field 1.5 million corn plants, and those corn plants contain 2 billion kernels of corn, spatially divided into 100,000 3x3 squares. And so somewhere in our database is 100,000 3x3 squares for this particular field, that you can go into our tools and you can zoom down, and we have a record for that. And we can take all of the kinds of different data that we get. We get data from planting, data from spraying, data from combining, harvesting in the fall, and they can each get layered over that same area. So you can come in and you can layer those maps, and um, you can compare them, and you can say, well, here's what we think we planted. Here's where our harvest is. Let's try to figure out some um, different data to tell us different things. And we can also layer other kinds of data on it. So we can get weather data, and we can get soil data from the USGS, and we could get soil sampling data, maybe that the agronomist provided. There might be slope data we can also get. And so we can get all kinds of data, and it fits into the same format. And then you can query basically through that. So we can say, on this piece of earth, what's going on there? And some of our farmers, we have provide sharing relationships. So the thing I work on personally is a security of how farmers share data with other people, and most often like an agronomist or a seed specialist or something like that. But they might be working with their seed specialists, and they might choose to share data with that seed specialist, and then they can take that data and they can layer it in even more interesting ways. So if you were a genetic scientist working on corn breeds, and you might be able to want to say, hey, I want to see how this particular trait behaves when we have high amounts of moisture versus when it's very dry. Or I might want to see, does it do better in Minnesota than it does in Alabama? Is the amount of sunlight, is the amount of rain that we get impacting how this plant is behaving? And they can compare that across pretty large data sets, which is pretty cool. So when we're streaming this data in, and like I said, we use a lot of Kinesis streaming queues, which is similar to Kafka, and then in between those are these processors that are running either in Java or Scala, and um, that data comes in, like I said at the beginning, or not, kind of in the middle. As it's coming off the equipment, it's very raw, right, and it's very compressed, and we get this raw binary data that comes in. And so we have a process we call IMAT, which is ingest, model, enhance, and transform. So when we first get that, it'll be in a raw binary format, and it might come from a lot of different sources. So there might be streaming data that's coming in. It might be that a farmer doesn't have good cell reception, so they just collect it all on the equipment, and then it just comes in as one giant file by the time they get back to their back to the barn and they finally have Wi-Fi again. Or they might actually even put it on a USB stick and walk it in to the house and plug it into their computer and upload it from there. We also have data coming in from competitive equipment, so you don't have to use John Deere equipment or displays on your tractor. You can use competitive equipment, and we can process a lot of those files as well. So we get that raw data in, um, and the first thing we do is just ingest it. Like, we get the data, let's figure it out. What kind of data is it? Let's put it where it needs to go for the next phase, which is to model it. So we take, no matter where it's coming from or what format it's in or how fragmented it is, we turn it into a common model that's the same for everything. And that's kind of step two. Then we get to the enhance phase, which is where we take that data and we start to make calculations and different projections with it. So, for example, miles per hour or kilometers per hour, speed, velocity is not something that's explicitly in the data. Nowhere do we say when the tractor was at this point in time, it was going 25 miles per hour. We can infer that it is going 25 miles per hour because we do know that's geographical space between where it was at this point in time and where it was in the next point in time. And so then we can very easily figure out not only how fast is it going, but what direction was it going in. And so that's an example of something we might enhance that data with. And there's a whole bunch of different things that we do calculations and start figuring that stuff out. Then after we've kind of, um, you know, beautified the data, it goes into the final stage, which is our transform phase, where we take that data that is now meaningful and has a lot of cool, interesting bits of data in it, and we do stuff like we make maps, and we make reports, and we format it into that trestle, um, and we put that in our data store. Now we've gone back and forth um, many times. I think we are on our essentially um, fourth version of this, especially of the transform part. A lot of the earlier phases of this haven't changed a lot, but transform has changed quite a bit. Our data lake that this goes into is over 40 petabytes. And I'm willing to bet that after we're done with this harvest, we'll be well over 50 petabytes. Um, and so, in order to be able to store and efficiently get back and report on 50 petabytes of data, um, it's a balancing act because 50 petabytes of data is really expensive and to store. Even at Google, even when you think, or not Google, at Amazon or Google or any of them really, Azure, um, a lot of it seems pretty cheap when you look at the price tag like up front, but once you got 50 petabytes in there, it gets really expensive. And there's also a performance trade-off. So we've kind of gone back and forth tweaking it with which is more important. You know, the cost of the storage versus the performance. So we can make stuff, we can pre-generate lots of stuff, and we can put it in storage, and it'll be blazing fast when you try to get it out onto a phone or a computer or something like that. Um, but if it but it might cost too much, and so those are considerations we have to make. Or we can do that calculation at runtime, but it's going to be slow. And so we've tried to figure out kind of, well, what's the best thing? Do we need to store? Do we need to pre-generate everything? Or do you always need to have a pre-generator? Are you really going to go back and look at maps from 10 years ago? And we do have people who have 10, 15 years worth of data in there. And um, and so maybe we can only pre-generate the stuff that we know you're going to look at, or we can assume you're going to look at right now. And we can figure that out with a lot of analytics. We could throw machine learning at it to figure out exactly what you want to do. But I think we've hit kind of a sweet spot right now. So we've got a pretty good balance between that performance and that cost. Um, so we have a system called Operations Center, and this is where all of this stuff gets fronted. So there's lots of tools in it to be able to see. You can open it up, and you can see where all of your equipment is at the moment. Um, the first thing that I worked on when I came to John Deere is I worked on remote display access, which is part of this. So that is where somebody can actually remote into the tractor, um, as long as it has some amount of cellular connectivity. This is a huge deal for our dealers because you know, a large piece of equipment in particular is a single point of failure, right? If it breaks down and you're in the middle of harvest, that's a big deal for a farmer. They need to get that equipment fixed, and they don't necessarily want to wait for some tech from the dealer to be able to drive all the way out to their farm. They might live far away. I know of dealers in Texas that actually have planes, and they will fly to their to the farmers because that's how big of a distance they're covering out in West Texas, where they do a lot of cotton. Um, and so with remote display access, they can just remote directly into the equipment, see what's going on, say, oh, you just have to change this number over here or tweak this setting, and then you're good to go. Saves a huge amount of time. And with COVID, what we found is that it's getting used even more. We had like the biggest year we've ever had with remote display access. Hugely popular feature. I'm really proud of that one. Um, And you can also see, like I said, the exact location, where the equipment's going. You can have little breadcrumbs which show where it's been, how fast it's been going, what kind of operations it's going. There are some people who have pretty big farming operations where they have lots of farms, or they might be doing custom farming, which is where um, some farmers, they own the farm and they get the profits from the farm. They don't actually do the farming. They hire someone to do that for them. And that's a strategy you can do. You're not going to make quite as much money because you're going to have to pay someone else to do the farming for you, but you take the total profits. Um, the people who do those custom farming operations usually do it for a whole bunch of people, so they might own quite a bit of equipment. Similarly, if you're an ag retailer, like at um, a elevator, they provide services. A lot of farmers don't want to like own a sprayer. They might not need it that often. So rather than owning a sprayer and having to maintain that, they'll just hire someone to come and do the spraying operations for them. And so those people own a lot of pieces of equipment. And so they want to be able to have a manager who can be able to pop open a map and see, where's everybody that is working for me? Where are they and what are they doing? And do they need any help? Do I need to send a grain cart over to this farming operation that's happening over here? How can I optimize the logistics of all that's going on? Um, and so, you know, there's you can have all of this. You can share your data. You can form those relationships. You can have a relationship with your dealer. You can have a relationship with your ag retailer. And you can use all of our tools. You can also use other people's tools. We don't require you to use our stuff, and most of the data that we have is available through APIs, through public APIs that anybody can use. And this is the other part of things that I work on personally, is the security of those APIs. So if you go to developer.deere.com, I'm not sure if I have a slide yet. We have a website, developer.deere.com. You can go, you can create an application. You can gain access to those APIs to be able to get all or most of the same information, and to be able to either contribute things into that data, maybe provide additional analytics, additional insights, or pull it out and put it in your own tool. We're fairly agnostic about it. We will intend to allow, like I said, um, most of the data that we have internally is also available externally in one form or another. And we have several hundred integrators with that platform. It's mostly REST APIs. We are starting to experiment with GraphQL internally. We don't have any public GraphQL right now, but it's a hot topic inside, and we've got some internal APIs that are using it. So that's pretty exciting. And then one of the other things my team oversees is OAuth, kind of how the nuts and bolts of the security framework work. So how do you get access to those APIs, and what authorizations do you have? And we have over 2,000 APIs that process over 10 billion requests per year. So it's a fair bit of traffic. So that's a fun thing, and you can do it. We're working on trying to get a better sample data set. If you go and set up a client, an API client today, you can have access to the APIs. You're just not going to get much data out of it. We're working on getting maybe some cooler sample data that people can play with. Or if you've got a tractor, you can go generate your own data and throw it out there. So there's one other thing that I wanted to bring up. I did not have a slide for it, but this group I think would appreciate it. We are experimenting more and more with machine learning. We have another kind of subdivision of ISG even that's in Silicon Valley, called Blue River, and we're working on a machine learning to identify, have a sprayer be able to identify uh, the difference between weeds and plants, basically. So we can have a sprayer go through and um, and be able to identify, hey, that's a weed, that's a plant, spray the weed, kill that. Um, and that would allow even more than just as the GPL coordinates of uh, of things on the ground, of being able to look at it. We think over time we could reduce um, herbicide use by possibly up to 90%, um, by being able to micromanage exactly where we're spraying. And, who knows where we can go for that. Mostly it's concentrating on herbicides at the moment. Maybe we can identify bugs. Maybe we can have little Terminator robots that go through and kill harmful insects. Um, Lots of really cool and fun things that are kind of going on in that space. So that's kind of the extent of my presentation. I'd be happy to take any questions, um, or if you don't have anything right now, you can always hit me up, and I would be happy to have a one-on-one conversation.